So here we are actually going to calculate an equilibrium constant from the equilibrium constant expressions that we write ourselves. Okay, so here we're given a reaction. Phosphorus and bromine react to form phosphorus tribromide, and here's the reaction there. They balanced it for us. You always want to make sure that the reaction, the chemical equation for the reaction is balanced before you proceed. And they say that a chemist finds that at a certain temperature, the equilibrium mixture of phosphorus, bromine, and phosphorus tribromide has the following composition. So what that means is this chemist set this reaction up. We don't know what the starting concentrations of this, and this were. Okay. If he started with these two reactants, of course, he wouldn't have had any of that to begin with. We don't know what the initial concentrations were, but we do know that at a constant temperature after the reaction went for however long until it reached equilibrium, that these were the concentrations of our two reactants and our product at equilibrium. So we know what that means at equilibrium. It doesn't mean the reaction stops. It means that the forward and reverse reactions are happening at the same rate. So there's no net change in our concentrations. So our first step is going to be to write the equilibrium constant expression, and then from that we can actually calculate Kc after plugging in the equilibrium concentrations. Okay, so let's write our equilibrium constant expression. Kc is equal to, products go on top, and here, even though these are gases, notice that the concentrations here are molar values, so in the units of concentration units of molarity. So that's why we're using Kc. In the past, we were using Kp when our substances were gases, but here the concentrations are given as molarity, so we're going to use Kc. Okay, so Kc is equal to the concentration of phosphorus tribromide to the fourth power divided by the concentration of phosphorus times the concentration of bromine to the sixth power. Okay. Now our next step is to substitute our concentrations here, because again, this represents equilibrium. So at equilibrium, the equilibrium constant is going to be equal to this concentration at equilibrium to the fourth power divided by this concentration times this concentration to the sixth power. So these concentrations are not just any concentrations, but equilibrium concentrations. Now, when we did this before, but we were finding Q, where Q was equal to the same thing, let's understand that those concentrations that we used to find the reaction quotient were not necessarily equilibrium concentrations. We were plugging them in to see where we were. Was it at equilibrium or not? So these concentrations, as they're equal to Kc, are going to be the equilibrium concentrations, okay? So if I take the equilibrium concentration of phosphorus tribromine, it's 0.5. Kc doesn't have units, so I'm just going to omit putting the capital M there. This is raised to the fourth power. It's going to be divided by 1.3 times 1.9 raised to the sixth power. Okay, so let's put this in a calculator and see what we get. So what I get for Kc, in this case, if they're going to have us round to two significant digits, it's going to be really small. So rounded to two significant digits, this would be 0.0010 or 1.0 times 10 to the minus 3. So what that means, because Kc is so small, it gives us an idea about the nature of this reaction. And this reaction heavily favors the reactant side. So at equilibrium, as you can see here, the concentrations of our reactants is going to be greater than the concentrations of our product. Because Kc is so small, the formation of reactants is more favored. And so, again, this is our answer.